there guys, in this video I wanted to cover 3 common torque problems, not to only solve the problems with you, but to show you a general framework that will allow you to solve pretty much any torque problem. Now this is not only helpful if you're in AP Physics, but also pretty helpful if you're taking any class that's currently doing rotational dynamics, torque, and anything along those lines. These are problems that come up pretty often on most tests and quizzes, let alone the actual AP exams. And so what I've done to find these questions is I've gone to the question bank, the NerdNotes question bank, and I've basically filtered out through the rotational motion topic. And I've picked out 3, again, common problems that you're likely to encounter, and we'll go ahead and just take a look at them right now. And so the first one, again, is a static problem. It's going to be where there is basically zero net torque. It's in rotational equilibrium. And so we'll go ahead and do this one here. We'll also do one that's not in rotational equilibrium. So this is going to be like a pulley system, for example. In this case, they're asking us to find the acceleration. And then another common problem is going to be of objects that are rotating down an incline. So this is what we refer to typically as rolling problems. And in this rolling problem, they're going to ask us to find the coefficient of friction on that incline. Now, before we actually solve these, I quickly want to show anyone that's in AP right now what these problems are going to look like on the actual FRQ section, at least. And so, again, this is a beam problem, pretty much almost identical, if not easier than the beam problem that we're going to solve today. Here's another one. This is dealing with a pulley, and this is a single block pulley. Once again, even easier than what we're going to solve today. And then here's another one that's actually going to be a static problem, but it's a pulley problem that's trying to maintain static equilibrium. And then we have one more problem, and this is going to be a rolling problem where a wheel, in this case, is rolling down a ramp. And so if you're looking for these types of questions, just quickly sort it out by the rotational motion unit. I've already done all that sorting for you, and I'll go ahead and paste this the post link to this in the description of the video. So that way you guys can quickly access it and start solving these rotational problems after you're done watching this video. So let's go ahead and start with this first problem, the bear walking on the beam. To solve this problem, the first question it was asking was to draw an FBD, and regardless of if it asks you to solve for the FBD or draw an FBD, you want to do it regardless. And the reason we do it is because without a proper FBD, it's almost impossible to get the correct answer. And so what I'm going to do is I'm going to start with the actual beam, and I'm always going to actually mark the hinge point. So whether you're doing a FBD of a ladder, in this case a beam, you always want to mark the pivot point. I'm going to actually go ahead and just start drawing all the masses that were present in the diagram. And so the first mass was going to be the mass of the actual basket of goodies. So I'm going to draw that as the weight of the basket of goodies. I'm also going to go ahead and draw the weight of the actual beam itself, M2G. And in this case, I'm using number subscripts. If you want, you can use letter subscripts like G and B for beam and so on and so forth. But yeah, I'm just going to use a number subscripts just to simplify it a little bit. And then the last weight acting on the beam was the actual bear itself. So let's call that M3G. And these were all the weights. And now we can actually go ahead and draw the tension force that we saw that was present. And that's going to look like that. And at this point, most people will say, okay, well, this is rotationally balanced out. We can go ahead and move on. And while that is true, this is technically rotationally balanced. We have one torque caused by the tension that will go counterclockwise, and we have 3 torques that will go clockwise. And so technically this is rotationally balanced. However, linearly, it's not balanced because, as you can see, tension will have a component. And let's actually go and draw these components. One component will point up and one component will point to the left. And so as you can see, there's a force that points to the left. And so therefore, this would be accelerating to the left if we left it as is. And so what we want to do is we actually want to counter that leftwards tension force with a force that goes this way. And where does that force come from? Well, it comes from the hinge itself. And so in other words, I'm going to label that as hinge horizontal force maybe. Okay. Now, we might be considering that we're done here, but again, we are still imbalanced almost. So we have a force that points up here and 3 forces that point down here. Well, there's no vertical force up here to hold the beam up on this side. And so what holds the beam up on this side? Well, you guessed it again, it's the hinge force that's acting vertically this time. And so we're going to put hinge vertical force maybe. And these are just the components. So you really want to be drawing the full total vector. And so what I'm going to do is I'm just going to combine these 2 vectors and sort of draw the full hinge force, kind of like that. Okay. Okay, awesome. Now that we got the diagram, now we can actually go and start solving for tension. Notice that we can't actually use linear forces to solve for tension, just because if we did use linear forces, then we would have to start taking into account the vertical component of the hinge force and the horizontal component of the hinge force, which they didn't give us in the problem. So in order to completely avoid using the hinge force at all, what we can do is we can use rotational motion. So instead we can use tau net is equal to I times alpha. And the reason we use this is because at the actual hinge, the lever arm, the distance away from the hinge, is effectively 0. And any force multiplied by 0 is 0. So in other words, the torque caused by the hinge itself is effectively 0. And so I essentially am able to get rid of the hinge force and not have to include it in my formula. Okay, so what are the torques that are being caused? Well, one of the torques is being caused by this component of tension. Assuming that we were given, I believe we were given this angle right here, which corresponds to this angle. So I'm going to mark that in here. So we were given that tension sine of theta, so T sine of theta is going to be my first force multiplied across my lever arm. Again, lever arm is the distance away from the pivot point, so that's going to be the length of the beam in this case. So T sine theta times the length of the beam, that's my torque caused by this component of tension. Next, we have 3 more forces that causes torques in opposite direction. So this is going to go clockwise. And because we're going clockwise, I'm actually going to be subtracting those torques. And so let's start with M1G. So M1G, again, multiplied by the lever arm, the distance away from the pivot point. Again, that's going to be L. That's going to be my torque caused by that first weight, minus this torque here as well. So M2G times half L. So M2G times half L. And I honestly didn't really explain why it's at the center, but whenever you draw the weight of the beam or the rod or whatever the actual platform is, you always want to draw it at the center of mass because that's where all the mass is concentrated. So that's why the distance from the pivot point is actually going to be half L. That's what I put here. And then the last force is going to be M3G multiplied again by the lever arm of 1 meter. They gave this to us in the problem. They said the bear was 1 meter away. And so M3G times 1 is just simply M3G. So minus M3G. Okay, awesome. And this is all going to be equal to 0 because there's no angular acceleration. So this is the beauty of static problems. You don't actually have to worry about this piece right here. All right, again, we want to find tension, and honestly, at this point, I'm not even going to bother to find tension because I think you guys would know what to do at this point. You would simply move all of these to the other side, and then just divide by sine theta L, and then you have your tension. And actually, just to show you one more step, we might as well go ahead and do it. So I'm going to do it. Sine theta times L is equal to M1GL plus M2GL, or actually half L, plus M3G. And so one thing we can possibly do straight off the bat is just eliminate the L, divide by L here. And we can also possibly eliminate, or at least factor out, the G from the equation. And so the final equation for tension is going to be T is equal to G over sine of theta times M1 plus M2. I guess that should be half M2 plus M3. Okay, there you go. So there's your final formula for tension. And again, the whole point of doing physics is to derive equations. It's not necessarily to plug in numbers because that's the easy part. And so here is your final equation for tension. And honestly, if you can sum up forces just like the way we did it here and then apply it rotationally just like we did it there, that's all you really need to do. Now, the next question is slightly trickier, and that's to find the actual hinge force. So in order to find the total hinge force, we need to find the components of the hinge force first. So we need to find HH and HV. And so let's go ahead and actually do that. Let's find the horizontal hinge component. And the way we can do that is simply by setting this component of tension. So the horizontal component of tension, that's going to be T cosine of theta, minus the horizontal hinge component, which points in the opposite direction, is equal to MA. So again, this is coming from F equals MA, right? Newton's second law. And once again, there's no acceleration. It's in equilibrium, so we can set that equal to 0. And so what we really are saying is that T cosine of theta is equal to HH. And then to solve for h of v, what do? We do the same exact process, but in the vertical direction. So we say hv plus t sine theta minus m1g minus m2g minus m3g is going to be equal to 0 because it's an equilibrium. Okay, and then you just solve for hv. Then once you have hv and once you have hh, you can use Pythagorean theorem to combine the two and find your resultant vector, which is the hinge force. Okay, so that's how to solve this kind of static equilibrium problem, and honestly, they're all going to be more or less the same. All right, so this next problem is going to be a pulley problem. There's going to be two blocks, and it's connected via a rope over a pulley that has a radius of 0.1 and a mass of 2 kgs. Now, the problem doesn't state this, but usually pulleys are cylinders or discs, and so they have a rotational inertia of 1/2 mr squared. Now, again, if you're taking the AP exam or even if you're in an in-class test, they normally would tell you this. The pulley is free to rotate about the axis, the system is released from rest, and the block of mass 10 kg starts to move downwards. Assuming the coefficient of kinetic friction between the pulley and the rope is 0.2, determine the acceleration of the system. So the first thing I'm going to do is obviously draw an FBD, because that's pretty much what you want to do for pretty much any torque problem. So we have a mass of 5 kgs and we have a mass of 10 kgs here. I'm going to draw it like that, and I believe the pulley itself was 2 kgs. But I'm also going to draw it in separately as well. So I'm going to draw the 5 kg block like this. And when I do that, I'm going to make sure to start with that 5 kg block. So M5G. In fact, I can probably just maybe eliminate that and just put 5G for the weight. And then we're going to have tension that points upwards. And notice how I drew that tension, and I'm going to call that tension 1 actually. Notice how I drew that tension bigger than the weight. And it's because that mass is going to be accelerating upwards. The next thing I'm going to draw is the pulley itself. And again, if you're following this order, it should be pretty easy. This is going to be tension 1 that points down. And I'm going to try my best to actually match it with the length I've already drawn here. So this looks a little bit short, so let me go and extend it a little bit. So maybe just like that. There we go, tension 1. And before I give you the answer, pause the video for a second and ask yourself if the tension on the other side should be the same, should it be shorter, or should it be larger? Okay, so if it were to be the same, so if tension 2 was the same, then what would happen is that there would be no net torque essentially, right? So you would have a torque by tension 2 and you would have a torque by tension 1, and they would just cancel each other out. So the pulley itself wouldn't rotate, and we basically don't want that. We actually want the pulley to rotate, so we need a net torque, and the only way to have the net torque is if tension 2 is actually bigger. So now that tension 2 is bigger, we're going to have a net torque, which will cause the pulley to rotate in a counterclockwise fashion, or actually in this case, a clockwise fashion. Okay, and then the last block you want to draw is that 10 kg block. And again, we're going to draw the tension. So starting with the vector that we already have, we kind of want to match it up as close as possible. So that looks about right, T2. And then of course you want to draw 10G, and you want to draw it much bigger than T2, right? So once you got that FBD, and again, it's super important that you nail this. If you don't, it's pretty much impossible to get the problem right. But once you get this, what we can start to do is now we can actually start to make a few equations. Let's actually start with the pulley itself. So we can make a net torque equation. So we can say tau net is equal to I times alpha. And by the way, if you want to start by making an equation with this block or this block, that's also perfectly fine. You really come to the same point either ways. And so if you are starting with the pulley, what we can do is we can say, okay, the bigger torque minus the smaller torque. So the torque caused by T2 is T2 times the lever arm. So it's going to be T2 times R minus T1 times R is equal to I times alpha. Like I said earlier, the moment of inertia of a disk or a cylinder is usually going to be 1/2 mr squared. You're not really expected to memorize this. They usually give you this. And so we can go ahead and substitute this into our equation for I. So I is going to be 1/2 mr squared. And using a little bit of foresight, we know that we can leave this as alpha, but I would much rather change it to linear acceleration because these blocks deal with linear accelerations too. So we want to kind of get everything into a similar term. And so how do we do that? Well, we know there's a relationship between linear and angular, and that's going to be linear acceleration or tangential is equal to alpha times r. And so therefore alpha is really going to be linear acceleration over the radius. And so again, instead of putting alpha, I'm going to put a over r. Okay, so that way I have in terms of linear acceleration. Okay, cool. One thing you might notice is that all the r's will cancel out. And you're left with basically T2 minus T1 is equal to 1/2 ma. One thing I forgot to actually do is label the mass of the actual pulley itself. So I really should be calling this M3. So just to backtrack a little bit here, M3 and M3. Okay. All right, awesome. Now, one thing you'll notice is that we don't have tension 2 or tension 1, but we do have FBDs for it, so we can go ahead and make some more formulas. So what I'm going to do is I'm going to give myself a little bit of a gap here and go down to the next page and make a formula for this one first and then this one second. So the formula for the block on the left is going to be T1 minus 5g is equal to mass times acceleration, and the mass is 5. So we can put 5 times acceleration, and then I can solve for T1. I can say T1 is equal to 5g plus 5a. Ideally, I should have probably left these in terms of a variable, so like m1 or m2, but I already have the number in there, so it's totally fine. Okay, making an equation for T2 now. I'm going to do the bigger vector, so 10g minus T2. So let's do this here. 10g minus T2 is equal to ma. Again, the mass is 10 times acceleration. Okay, and then we can solve for T2. So T2 is going to be equal to 10g minus 10a. And there you go. Okay, now what we can do is we can actually go ahead and start substituting these two back into this. Okay, so that's going to look something like this. It's going to be 10g minus 10a minus 5g minus 5a is equal to 1/2 m3a. Awesome. So now, as you can see, our little bit of foresight from earlier worked. So we swapped alpha out for acceleration, and now, as you can see, all our variables, all our acceleration variables are now in terms of linear acceleration. And so what we can do now is we can go ahead and move all the linear accelerations to one side and then solve for a. Let's go and do that. It's going to be 10g minus 5g is equal to 1/2 m3a plus 5a plus 10a. And lastly, what I'm going to do is I'm actually not going to simplify this any further. I actually want to leave it as it is. And all I want to do is just factor out the a. So I'm going to get 1/2 m3 plus 5 plus 10. And so the reason I'm going to leave it like this is because I told you from the start, I'm actually here to help teach you how to derive these equations. So that way you can use it for anything. Now, the cool thing about this is that if you want, you can, on a test, you should probably go ahead and do all the derivation steps. But what you'll notice is something very interesting. You'll see basically in order to solve this problem, what are we really doing? What does this boil down to? Well, we take the weight of our force that accelerates the system, so 10g is the weight of the bigger block, minus the weight of the smaller block, the force that retards the system. And really, to solve for acceleration, all we need to do is just divide it by the total mass. So this is really the mass of the small block, mass of the big block, and then the mass of the pulley itself. But also, just with a little caveat, we multiply by half. And so really what I'm trying to say is that this formula that we just derived is really just a formula that solves for that uses the same formula as the net force of a system. So in other words, the force that accelerates it minus the force that decelerates it divided by the total mass. I'm not going to explain that too much. If you understand what that means, great. If not, I'll link another video below where actually I solve multi-body systems using basically net force of a system. Then maybe that explanation will make a little bit more sense. All right, so the next problem is going to be a rolling problem. And let's go ahead and take a read through this together, and then we'll solve it again using FBDs and just a net torque equation. So the moment of inertia of a uniform solid sphere is about 2/5 mr squared. The sphere is placed on an incline and released from rest. We need to determine the minimum coefficient of friction between the sphere and the plane with which the sphere will roll down the incline without slipping. Write your equation in terms of theta and any other fundamental constants as needed. And then part B says if mu were to be 0, what would be the speed, or would the speed of the sphere at the bottom be greater, smaller, or the same as in part A? Okay, so I'm going to start by drawing an FBD, and what I'm going to do is I'm going to exaggerate this diagram so that way you guys can see it a little better. And the first thing I'm going to draw is the weight component, so this is mg. I'm going to draw my normal force starting from the ground, or the surface in this case, and pointing perpendicular to that surface. And the last component I'm going to draw is actually the force of friction. So that's going to originate from the surface and point this way. And maybe actually I'll draw that a little bit smaller, like that. And in case you're wondering, this is going to be static friction. Okay. And the reason it's static friction is because if it was to be kinetic friction, that would imply that it's sliding down the ramp and not actually rotating. In this case, what static friction allows us to do is basically create a torque. So this is our lever arm right here, the radius of the sphere. We apply that force, and it's going to cause a torque that will then spin the actual sphere in a counterclockwise manner in this case. And then, of course, that's what's going to cause it to roll down the ramp. Before we actually move on to solving via equations, just double check if everything looks right. We know we have components of mg that will point down. That's going to balance normal force out, so that checks out. And then we're going to have a component of mg that points down the ramp. And of course, we know in order for it to accelerate down the ramp, there needs to be a net force. And so in other words, this force should be bigger than Fs. So that roughly looks about right. So I'm just going to leave it like that. But just keep that in mind as we go into actually putting this into equations. So the first thing I'm going to do is I'm going to solve this traditionally with linear forces. And so I'm going to say F net is in the x direction is equal to ma. And we know that the net force is going to be mg, the x component specifically. So it's going to be, and let me actually just draw this out here. So it's going to be this component and then this component. And so this is the component that we're concerned about. And the angle that we're dealing with is going to be up here. And so this is really the sine component of mg. So it's going to be mg sine of theta. That's going to be basically pulling the sphere down, while static friction is going to retard that motion, so Fs. And that's going to be equal to ma. And what you can see straight off the bat is that we are kind of running into an issue. Normally, we can just plug in the formula for Fs, and then there's going to be our mu value inside of that, and then we can just solve for that. But the problem is that we don't actually have acceleration. So what do? Well, now we need to have a second equation, and that second equation is going to come from torque. So now we can say something like torque net is equal to I times alpha. And again, like I already pointed out, the torque is coming from the static friction. And it's specifically going to be Fs times r, that's my torque, so Fs times r, is equal to the moment of inertia of the sphere, which is 2/5 mr squared, times alpha. And again, instead of putting alpha, I'm going to replace it with a over r, just because I'm using a over here. I'm using linear acceleration over here. And if we're going to be plugging and substituting equations into each other, we all kind of want it in similar terms. So I could have either changed this to alpha, but in this case, I chose to change this to linear acceleration. Okay, so notice another thing, all the r's cancel out on this side. So Fs is going to be equal to 2/5 ma. And if you really want, you can actually solve this for acceleration. So acceleration is going to be equal to 5 over 2. Maybe I should write it this way, actually. So 5 Fs over 2m. There we go. And now what I can do is I can go ahead and plug that equation into this, and that effectively eliminates our acceleration variable, and then we can go ahead and solve for Fs and the mu variable that's within Fs. Okay, let's go ahead and do that. Let's start doing this in a different color now. So mg sine of theta minus Fs is equal to 5 Fs over 2m times the mass. The masses cancel out here. And then I can say mg sine of theta is equal to, and I can move Fs to the other side. And if I do that, that's going to give me 7 Fs over 2. And now what I can do is I can go ahead and start to replace Fs with the formula for the static friction. And that's going to be mu times n, so mu times the normal force. And instead of putting n, again, we know that the normal force is being balanced out by the y component, the vertical component of weight of the sphere, and that's going to be mg cosine of theta. So instead of putting n, I can replace that with mg cosine of theta. So that's what I'm going to do. It's going to be mg cosine of theta. Notice how the masses, or the weights in this case, elegantly cancel out. I'm solving this for mu, so I can go ahead and move the 7 over 2 to the other side. So it's going to be 2/7 sine of theta over cosine of theta is equal to mu. And of course, sine over cosine is just tangent. So we can say 2/7 tan of theta is equal to mu. And so there you go. There's your final derived equation. And so you really had to do a lot of work just to boil it down to a very, very simple formula. And then the last part of this question was asking basically if you were to have no static friction, so if you were to eliminate that, and if it was just to slide down the ramp, would it have a greater speed at the bottom? Now, I'm not going to derive that equation in this video, but basically that has to do with energy. And the short answer is that, yes, it will have more speed at the bottom, because now that it's not rotating, because there's no static friction, more of the energy can actually go to speeding it up translationally, and so therefore you're going to have more speed at the bottom. All right, guys, hopefully that video was helpful. Just to recap here really quickly, most of these problems, if not all of them, can be solved with an FBD. And just doing a combination of both linear forces and rotational forces, and then combining those equations up together.